Hey kiddos, and welcome to chapter 12. There are 3 installments for chapter 12, which is talking all about energy. The first one is talking about activation energy. So activation energy is pretty cool. It's pretty easy, and it's very easy to see it in a potential energy diagram. And let's get started. So chemists theorize that for a reaction to occur, the reacting particles, which are atoms or ions, must collide with one another. And this theory, now this is just called a theory, kiddos, it's not a law, is known as the collision reaction theory, and we've learned about that before. So let's talk about the reaction progress. Why do some chemicals react faster than others when all other variables are controlled except for the type of chemicals? Example, magnesium reacts much faster with hydrochloric acid than zinc. There has to be something about the actual, in this case, metal itself. Why do some reactions need an initial input of external energy to start? An example of this, a match is needed to start the combustion of a hydrocarbon. You need to start a fire in order to continue a fire, but when a fire starts, oxygen is its main fuel, but there has to be something to start that. So here we have the collision reaction theory, diving deeper into this. A chemical sample consists of entities. Entities could be atoms, ions, or molecules that are in constant random motion at various speeds, rebounding elastically from collisions with each other. So these things are colliding constantly. And what happens is when you get these collisions, cool things happen. You get new compounds, new things being formed. A chemical reaction must involve collisions of reactant entities. So, an effective collision, kiddos, requires sufficient energy. So there needs to be the right amount of energy. Collisions with the required energy have the potential to react. We have this thing called an activated complex, kiddos. So you have carbon monoxide, an example, nitrogen dioxide. They're going to be colliding with each other to form this jumbled up mess. And this activated complex is important, and all you have to know all you have to know is where it is in an activation energy diagram. Okay, that's all you have to do is be able to point it out, and it's super easy. And then what happens is products are formed if there's sufficient energy, and there's also a second stipulation. There has to be the correct orientation. So if you have the correct orientation and the required energy, you're going to have products being formed. Okay? If you don't have sufficient energy or you don't have the correct orientation, you're not going to have products formed. You're just going to have not a lot of stuff. Ineffective collisions involve entities that rebound elastically from the collision. And when they rebound elastically from the collision, they don't actually create um, as many products as they should, or no products at all. See, here we have carbon monoxide and nitrogen dioxide, and at the end of the day, you have the same. So nothing actually happened because either there wasn't enough energy or the correct orientation wasn't achieved. Okay, cool. So remember we talked about the activated complex. Well, an activated complex is an unstable arrangement of atoms that exist momentarily at the peak of the activation energy barrier. So this happens for a quick second, and they belong here at the very top of this activation energy diagram. Now this here, kiddos, this is your potential energy diagram. Okay, it happens to be a step down. And then this is your activation energy. And activation energy is the minimum energy, the very minimum energy that colliding entities must have in order to react. This initial input energy may be in the form of heat, light, or electricity. So you need that bump of energy in order to start something going. Here's an example of carbon monoxide reacting with nitrogen dioxide to form carbon dioxide and nitrogen monoxide. And we'll notice here, this is our activation energy here. This portion here is just your potential energy diagram. And of course, at the very top is your activated complex. So the diagram on the right just tells us about the before and after. So here's our potential energy diagram, right, which you've seen before. What we're not told is like, hey, what energy is needed in order for this to happen? And that's the activation energy. Now, you can't guess what the activation energy is. There's no way of knowing that. But while there is knowing is if I give you a diagram like this, can you see where the potential energy diagram is, the potential energy portion, the activation energy portion, and the activated complex? Yeah, there's no way you can predict what the activation energy is at all. So here's the energy changes during the formation of hydrogen iodide. So this is a step-up diagram. Here's a potential energy diagram here, right? And here is your activation energy. And the activation energy goes from the reactants, right, all the way to the top of the activated complex. So draw energy pathway diagrams for a general endothermic, so a step up, and a general exothermic, so a step down reaction. Label the reactants, the products, enthalpy change, the activation energy, and the activated complex. So if you guys want to pause now, get that done so you have an idea of what that looks like, and I will post the answer. So here's the answer, kiddos. For potential energy changes during endothermic reaction, this is during an endothermic reaction, it's a step up. So here are the reactants, here are the products, and here's the activation energy and the activated complex, okay? And the activation energy goes from the reactants all the way to the top of the activated complex. So here's a potential energy diagram during an exothermic reaction. It's a step down. Okay, and the activation energy is still from the reactants all the way to the top of the activated complex. And you also have to tell me the change in enthalpy of the reaction. Just show where it is. You don't have to give a number, obviously. And your products, reactants, products. And that's it, kiddos. So activation energy, good times.